Right, so I'm going to share my screen right now. Share screen. I hope everyone can see. So as Yuri just said, the title of this presentation is Aggregation Patterns. So, como é que eu desconto aqui? Deixa aqui do lado. Aggregation patterns in systems composed of few magnetic particles. And as a subtitle, I have added this: how magnets and grains make fractals, right? So this is a work that we have published, me, you, and Francisco, we have published in the Journal of Magnetism and Magnetic Materials in the beginning of last year, right? So it's just a brief presentation on on the best results or the most surprising results that we have found in this research. So my name is Jorge A. I am a student of electrical engineering in the Department of Electrical Engineering at the University of Brasilia. But I have worked with Yuri in the Department of Mathematics for about 3 or 4 years. So most people are familiar. Do you know how I hide this on the top? Everyone can read this right now. Magnetic granular systems. So most people are familiar with the concept of grains or granular matter, granular materials for a more scientific jargon, and magnets, right? So in the left, we have an example, a simple example of what we're calling granular materials. So any system composed of discrete particles that interact via contact may be called granular material, right? So the motion of these particles that compose this kind of materials are usually independent, right? They may have, and they are followed by the contact rules that we model the system with, right? And magnetism is a very broad type of phenomena, right? We're talking about permanent magnets right here. So particles that have a fixed dipole, magnetic dipole in the center, and they generate a magnetic field. And because they generate a magnetic field, they interact with other magnetic field generated by external sources, right? So just a simple example, we have these balls that we find in children's playgrounds. They can be considered granular material. We have asphalt. We have grain crops, for example, right? Corn and all kind of sorts of grains can be considered granular material, right? And the sources that I have put for these images and for the rest of them, you can always find them in the bottom of the page, right? So we can combine these two ideas and get what we call magnetic granular material. So it's basically a bunch of little particles that have magnetic dipoles associated with them. So for short, we are using MGM. Right, so MGMs have found a wide range of applications, for example, in the fabrication of magnetorheological fluids and targeted drug delivery systems. So magnetorheological fluids are fluids that have some sort of fluid that has magnetic particles immersed in them, right? Usually in the order of micrometers. And because of that, the fluid responds to external magnetic fields, as you see here in the left side. And targeted drug delivery system, you can see the little mouse here. It may have some form of cancer, of anomaly, or some form of disease that can be treated with, or better treated, when you take the drug and inject it in a very specific place of the mouse, right? So these drugs can be delivered via magnets. They can be attached to magnets, and an external magnet can then target the drug to the specific local that you want to deliver the drug, right? So there are many applications. And in this work, we set out to model and simulate granular systems composed of few magnets. And that is because we believe that by understanding how 2, 3, 4 magnets interact with one another, how they aggregate, we can then better understand the macroscopic structures that may appear when we're talking about systems composed of many more magnets or particles, right? In this case, we're talking about particles in 2 dimensions, and in order to describe them better, understand the dynamics of aggregation and dispersion in the systems, right? So we use the discrete element method alongside well-established equations for dipole-dipole magnetic interaction and soft matter contact interactions. So the discrete element method is something that's very well established as well. We're talking about interpreting each particle as in a individual when we're talking about the equations that govern these kinds of systems, right? Dipole-dipole interaction and magnetic interactions that have very well established as well equations for this interaction. And soft matter, where it's as well, it's a very common method in modeling these kinds of systems, of granular systems. So the DEM consists of considering a set of forces and torques acting on each particle individually, then applying Newton's laws of motion, solving the resulting equations to obtain the evolution of position, velocity, and force for each particle. So basically what we have is that mass times acceleration is equal to the sum of all forces acting on each particle. We then can solve these equations that arise. There is one equation for each particle in the system, and that is that is where it comes from, or where the discrete nature of this method comes from, right? So the particle state description, each particle current state is uniquely described by its position, its velocity, and its magnetic dipole moment, or where the dipole moment is pointing, where the magnet inside the particle is pointing towards, right? This magnetic dipole moment in this case is fixed with respect to the body of the particle. And there are other static properties such as mass, magnetic dipole strength, stiffness of the particles, friction coefficient. All of these little things are better addressed in the full article, right? So this is an example, a geometrical example of how the setup of the systems is given. So we have 2 particles here, M1, we have another particle M2, right? So they have a distance vector here, which is given by the difference of their positions, right? And then because they're interacting via magnetic forces, these 2 forces, F21, F12, appear and try to move these particles. There is also a torque associated with these forces, with these magnetic interactions. And when particles eventually get in contact, there's also a set of forces that we call contact forces. So here are the equations that we have. I have not placed the full description of all the little forces that compose the full set of forces that we have for each particle. But as was said before, the governing equations in our system are obtained by applying Newton's laws of motion to each particle. That is, the summation of all forces acting on particle equals the product of its mass and acceleration. For a set of n particles, this gives us mass times the acceleration of the ith particle is equal to the summation of the magnetic forces acting on it, the normal force, the normal contact forces, and the shear contact forces that appear when 2 particles that get in contact. And as well, we have here the rotational dynamics of the particle, right? So the moment of inertia times the angular acceleration here is equal to the summation of torques acting on each particle. So we have a magnetic torque, we have a torque that appears because of shear forces acting on the surface of each particle, and we also have a rolling friction term that is associated that we need to adjust the model, right? Because the term here in the middle may vanish when particles are in contact and they have no velocities in the point, no relative velocities in the point of contact. But we know that particles may have no relative velocity in the point of contact, but still they have to feel some form of friction because of the bumps and imperfections in the surface of these particles. So this last term is an adjustment to encompass this kind of phenomena, right? So for the full set of forces and equations that are inside of each one of these forces, we may see the article afterwards. So a general description of the simulations that we have run for this article specifically. The simulation setup used for a system always considers no initial velocities and a given set of initial angular positions, as well as positioning particles in a regular n-sided polygon of side length L0, right? So what we mean by this, for two particles, it's very simple. We just put one particle here and another particle here with a given set distance apart, which is L0, right? And for three particles, we're placing them in the vertices of a equilateral triangle of side length L0. So the side length is given with respect to the diameter of each particle. So for these systems, we're talking about L equals 5D, right? In both the case of two particles and three particles. And after setting up these conditions, we integrate a system of equations with what we call the Verlet method of integration, which is also very usual for DEM models, up to a certain threshold, or up to a certain time t equals t, right? At the end of each simulation, so as I said before, we're trying to describe the aggregations, the kinds of aggregations that appear when we set these systems in motion. And so at the end of each simulation, we verify the configuration in which particles find themselves. For two particles, there are only two possible outcomes. Either particles are dispersed or aggregated, right? We have two particles here, one here, or they have collapsed and they are aggregated. For three particles, there are four possible outcomes, which this figure is described for us. So we can either have full dispersion of the system, we can have two particles aggregated and one dispersed, we can have then two forms of complete aggregation of the system. We can have particles in a line or particles in a triangular shape, which is most commonly called chains and rings in the context of magnetic dynamics, right? So magnetic particulate dynamics. So here we can attribute, in this work we found that we can attribute to each one of these configurations a specific level of magnetic potential energy. As you see here, so this is a random sample of simulations with random initial configurations for the direction of each of the three particles, right? So for a number of particles we're working with, these configurations can be uniquely described by the magnetic potential energy of the system. We don't know if that holds for n greater than 3, but we know that for 3, we can safely assume that if a particle has minus 2.1, more or less, unities of magnetic potential energy, then we can safely assume that the system is in the chain and three chain configuration, and so it goes. So this is the state of least magnetic energy, least potential energy. We expect the system, the configuration with the least of the lowest potential energy is the most common, followed by the triangular shape, then the other one, then the other one. So this is not exactly what we have found after we ran the simulations, but it's just some analogies that can be drawn from our intuition, right? So one of the biggest questions that we had when we started working on this problem was whether or not it was possible to predict each system's outcome. That is, if I have given you if it was given the initial directions of each particles, can we predict whether or not they're gonna fall into a triangular shape, into a three-chain shape, into a two-chain shape, into complete dispersion, or something like this, right? And as simply as this question may be stated, finding an answer proved to be, maybe not surprisingly for anyone who has done research in mathematics, very difficult, right? So this is probably our biggest result. It's just, I'm going to try and explain here what this diagram is all about. So for a set of three particles, there are three angles that we have to give in the start of the simulation: the angle for the particle, for the first particle, the second particle, and the third particle. So theta 1 is the initial angle for particle 1, right? And here we have a diagram that maps the outcome of each system, the possible configuration that it may fall into, to the pairs of theta 2 and theta 3 initial positions, right? So what we see here, the dark blue region corresponds to particles that have fallen after the simulation have ended, have fallen into a state of 3-chain, right? So 3 particles in a chain. The light blue region corresponds to particles that have fallen, for configurations that have initial conditions that have fallen into a configuration of triangular shape or a ring, right? The dark red region here that we have right in the middle corresponds to to systems that have completely dispersed, and the orange region corresponds to systems that we have 2 particles aligned and 1 particle dispersed, which is somewhere in between the system. It makes sense that this orange region surrounds the complete dispersion region, right? This counter that we have right here corresponds to the region. Inside this counter, we have the region of initial positive energy for the system. Outside of it, we have initial negative energy for the system. So it was expected when we first drawn these diagrams, we were expecting that configurations with energy, with positive initial energy, would lead us to dispersion, but that's not necessarily true, as we see here. So this is a very complicated diagram. We do not necessarily understand the structures that are here, but one thing we know for sure is that it's very complicated. So this is just a cut in the 3-dimensional space of initial configurations that we may present our system. So for theta equals 1, and here I have also plotted for theta 1 equals to pi over 12, and you can see that this diagram evolves, right? For here for pi over 6, pi over 4, pi over 3, pi over 5 pi over 12. So in steps of pi over 12, I think. So we can see that it evolves in some form of with some sort of smoothness, right? But we have not been able to find yet the mathematical tools that we need to better describe these structures that we have found here. It is expected in these sorts of systems to find chaotic nature, some form of chaotic nature. So 2 conditions that are very close to one another can lead to completely different states, as we see here in the boundaries of these regions, the dark blue region with the light blue region, the dark blue region with the orange region. So 2 very similar, very close initial conditions can lead to very unpredictable outcomes, right? Very different outcomes. And that's what most definitions of chaos encompass, right? So, and eventually we find them. There is almost no dispersion when a particle is completely upside, pointing upwards. And there is also a lot of symmetries here. My main goal with this presentation was to show that such a simple system can show very interesting structures, and also ask help to anyone that may think they know better tools to describe this system. So any questions are welcome. For a full description of equation, methods, and results, please refer to the full article. It was published in the Journal of Magnetism and Magnetic Materials, or contact us directly. So this is the email of Yuri, right? And I want to thank you very much for your time. I think that's it.
Thank you very much, Jorge. Am I wrong, or have you forgotten to show the videos?
Oh, yes, I have forgotten to show the videos.
Yes.
So just Yuri very kindly provided this. He's asking me this because he took his time to take these videos, right? So yes. Here we have 3 magnets. We can see they're more or less in a triangular shape here. And then if we let go of one of them, we can see that these 2 particles aggregate and wander off into the distance, right? And this is this set of magnets was what inspired us to do this work, right? And here we have a case of completely complete aggregation of the system, right? And this is what we're talking about when we say that there are many possible configurations for the system, right? We have as well another video of two-line aggregation here, right? And then these two particles wander off, right? I think that's it. I welcome any questions that you may have.
Thank you very much, Jorge. We are open for questions, perguntas em português, dúvidas, perguntas, comentários, questions, doubts, suggestions. We are open for questions now. Anyone?
Anyone?
So, Jorge, a quick question. Do you think that the videos that you showed, they represent a slightly different system from the one that you are simulating?
Yes,
so
yes,
that's
sure
a
do.
three-dimensional problem where
Yes.
the dipoles of the spheres can now take any direction in a three-dimensional world. There is friction with the rolling friction, so the particles can roll, they can slip, and many other more complicated dynamics. Question number one, do you think we can try and simulate three-dimensional systems?
Yes.
Question number two, do you think the mechanical properties of the contact can play a role on the eventual bifurcation diagram? And yeah, basically these two questions.
All right. So yes, I think there is a very natural generalization from the two-dimensional systems that we have simulated here to the to three-dimensional systems as the ones that I have shown in the videos. So there are some phenomena that we need to model better, right? For example, the friction model, the rotational dynamics become a little bit more complicated when we are not restricted to the plane, right? So, but the equations that we have here, they're very general, right? It's very easy to generalize them for 3 dimensions, and they have analogous in 3 dimensions in the current works that have been done in the area. So, I think that answers the first question. The second question was if the contact dynamics of the system may play a role into the bifurcation diagrams that we have here, right? So that is the answer to that question is yes, they play an important role, mainly when we're talking about the distinctions between lines or chains and rings or the triangular shape. So we're talking about the difference between the two states that have the least amount of energy. So before a system can collapse into a chain state or a triangular shape, it needs to first be in a line state. What I mean by this is that these 3 particles do not get into contact at the exact same time when we're talking about configurations or systems that have fallen into the configuration of triangular shape, right? So there first needs to be a contact between I'm going to start my video again here so you can see my hands. So first 2 particles get into contact, and then the third particles comes into contact with these 2. So it first probably gets into contact with one of these 2, and it collapses into the state of triangular shape. And the friction plays an important role, and the friction in the system plays an important role when these particles collide with each other, if they're going to fall into the triangular shape. But I believe, and we believe that for the distinctions between the complete dispersion, the 1 particle dispersion and 3 particle lines, the contact dynamics do not matter that much, because what dictates the evolution of these kinds of systems up to the point where all particles are in contact is the magnetic interactions between them, not the contact dynamics. So I think I think that answers the question.
Very good, very good. Thank you very much, Jorge. Any further questions, comments, suggestions? If anyone knows a good mathematical tool to help us understand the long time behavior of these systems, please come and say hello. And we are very much willing to understand how this evolution of the bifurcation diagrams occur, and how can we, based on the initial conditions, can identify the long time behavior of the systems, whether they will evolve towards an aggregated state, or will they remain in an eternal coordinated interacting non-aggregative motion, right, Jorge? This is a question that we need to, and I think we need proper mathematics here to understand that.
Yes, I agree completely.
Very good. So thank you very much once again. That was brilliant. Now we are going to have our second talk, our second speaker of the day, and I think it's Gabriel. Can you please organize your talk while we wait a couple more minutes till it's time to start? Very good. Hang on, I should stop recording.